Hello, welcome back to this first course in general physics. In this lecture, we will start discussing a new topic which is related to the motion of a rigid body. From now on, in this chapter, which will consist of 3 lectures, we will discuss the motion of an extended object which has not been discussed before. Previously, we have discussed the motion of an extended object under the condition or the constraint that all points of the particle move in the same way, and we have developed the general tools in chapter 4 to be able to deal with the motion of a system of particles, including rigid bodies, and we will apply these tools and principles to the study of the motion or rotation, actually, of the rigid body. So, in the beginning, we will, as usual, be concerned with the kinematics of the rigid body. We will focus our attention on the rotational motion of the rigid body because the translational motion has been discussed extensively so far. Even in the realm of discussing the motion of center of the system of particles, we have concerned ourselves with the study of the motion of the center of mass. We have not studied actually the relative motion of the different parts of the system relative to each other, which involves the rotation. So we will define the position, in which case we will define the angular position because we will be concerned with the rotational motion. We will then define the angular displacement and the angular velocity, and we will also define the angular acceleration in a similar fashion to what we have done in the case of translational motion. This will provide us with the tools for the description of motion of a rigid body, which is the rotational motion. This description of motion is the kinematics of rotation. Then we will, after we have defined these key points which are essential for the description of motion, we will use these definitions in order to arrive at or obtain the equations of motion for the rotating object. And we will consider as a simple case the case of rotation with a constant angular acceleration, just as we did in the case of one-dimensional translational motion. And then we will derive the relations between the linear and the angular variables, because there is so much similarity between the one-dimensional translational motion and the rotation of a rigid body around a fixed axis. So we will be concerned with the relation between the linear and angular variables. And then we will discuss the kinetic energy of rotation of a rigid body rotating about a fixed axis, from which we will derive the formula for what we call the moment of inertia of the object. We will define this quantity, and we will know how to calculate it. Then we will discuss the parallel axis theorem, which is a nice tool to know in order to be able to calculate the moment of inertia for the system in different geometries. And after that, we will start defining the dynamical quantities, the torque, which is responsible for the rotation of the object. We will then state Newton's second law of rotation. We will concern ourselves after that with the work of an external agent and the resulting rotational kinetic energy and the relation between the two, the work done and the rotational kinetic energy, just in a similar fashion to what we have done for the translational motion. We will then define a new quantity, which is the angular momentum. We will define Newton's second law in terms of this quantity, the general form of Newton's second law for rotation, and then we will deduce a formula for the angular momentum of a rigid body rotating about a fixed axis. And finally, we will arrive at the very important principle of conservation of angular momentum. The general motion of a rigid object, which is extended in three-dimensional space, as we have said in the context of discussing the motion of a system of particles, involves the translational motion, which is the motion of the center of mass of the body. So this translational motion is determined by using Newton's second law applied to the motion of the center of mass of the body. And also, the general motion of a rigid body involves, in addition to the translational motion of the center of mass, it involves rotation. So any object in general would be moving, having these two components of motion, which is rotation and translation at the same time in space. The rotational motion is determined by the relative motion of the different parts of the object with respect to the center of mass. That is the rotation of the object. In the beginning, we will be discussing the kinematics of a rigid body, which is the description of the motion of a rigid body, since the rigid body, as we mentioned, can be translating and can be rotating at the same time, as we have seen for this dancer in this slide. For the discussion of the kinematics of a rigid body, we have to define our problem. What are we interested in? As a simple example, like for the translational motion, we have discussed the motion of a single particle moving along a straight line, which is the one-dimensional motion. In this case also, we should pick up a similar problem, which is a simple problem, and we should consider the rotation of the object about a fixed axis. So the axis of rotation is not moving. The object is rotating with respect to the fixed axis, in which case the rotation is maintained in the same fashion, which is similar to moving along a straight line for the translational case. So this would be a simple problem, but in this case, the motion of one part of the object with respect to one another is ruled out in this calculation. We only consider the total rotation of the object with respect to a fixed axis, and the mixing between the translational motion that we mentioned and the rotational motion is ruled out, like in the case of rolling. If we have a ball that is rolling, this ball is translating in space, its center of mass is changing. At the same time, it is rotating about an axis that goes through the center of mass. So this rolling is a mixture, a motion that consists of a mixture of translation and rotation. Such motion will be ruled out, meaning we will reduce our problem to a simple rotation, which means that we will not be considering the motion in which the center of mass is translating in space. So this will be the problem of pure rotation around a fixed axis, which is similar to translational motion in one dimension. And this picture depicts the problem that we are concerned with, where we have a general object of a general form. That object is free to rotate around this fixed axis, which is z, that is going through its center of mass. And in order to study the rotation of this body, we have to define the position of the body as it rotates. But how can we define the position in the case of rotation? In the case of translation, the position that is changing is the position of the particle, the x position. In the case of rotation, what is changing is the angle. So if we focus our attention on a point at the surface of the body, we notice that this point is changing position, but it's changing position in an angular form. So if we follow the angle that this point makes, but the point cannot make an angle, the line, usually a line makes an angle with a reference line. So we select a reference line, and that reference line is usually selected as the x-axis. And in order to determine what is the displacement or what is the position of the object as time goes, as it rotates, we draw a reference line that is attached to the body, which is this red line, and we measure what is the orientation of this reference line with respect to the x-axis. So the angle that this reference line makes relative to the x-axis would be the angular position of this body. And this reference line can be chosen any line, not necessarily this line that we show, because in such a motion, which is the rotation around a fixed axis, all the points of the body are rotating in the same fashion and covering the same angle during the same period of time. So we don't care about the reference point, but we select a convenient one. And now we are ready to describe the motion of the body. As usual, we measure the angle between the reference line in the body, that's attached in the body, and the x-axis, which is the axis from which we measure the angle. the position. And this figure illustrates how the position is measured. This red line is the reference line attached to the body as it rotates, and this is the x-axis. In between them is the angle theta. Suppose that the point that we are tracking in the body, the point which we track its position, its angular position, is at a distance r from the origin. Then that point moves around a circle, a circular path, and the angular position theta that it makes is given by s divided by r, where s is the length of the arc between the x-axis and the point on the object. So this is the angular position, is equal to arc length divided by the radius, and the angle is measured in units of radians. That is, well, it's not really, radians is not really a physical unit. It's just a name to give the radial or the angular position in order to know how do we measure it, because the angular position can be measured in different ways. For example, we can measure it in terms of revolutions. How many times did the object go around the circular path? If it has gone 1/3 times, so the position is 1/3 a revolution, or 1/2 a revolution, or so. So this is the number of revolutions, or the fractions of revolutions. Could be a way of measuring the angular position of the of a point, a special point, which is the point that lies on the reference point, on the reference line that is attached to the object, which we use to measure the angular orientation. And there is another way of measuring the angular position, which is in terms of degrees, that we know that a full revolution is equal to 360 degrees. A yet third way of measuring the angular position is in terms of radians, where one full revolution is equal to 2 pi radians, where pi is the constant that is 22/7, which is 3.14 something. These are the ways in which we measure the angular position, and by relating these quantities, we realize that 1 radian is equal to 57.3 degrees, and this is equal to 0.159 of a revolution. So these are the ways to measure the angle, and the angular position theta of t, if we determine the angular position as a function of t, then we arrive at a complete description of the rotation, of the rotational motion of the objects. As we have discussed in the case of the one-dimensional translational motion, knowing x of t would completely describe the motion of the object that is translating on one dimension. Also, in this case, knowing theta of t is leads to a complete description of the motion of the rotational motion of an object around a fixed axis. The angular displacement, as usual, in order to define the different physical quantities by which we can define or describe the motion of the rotating object, we need to define the angular displacement, and the angular displacement is defined as the difference between the initial angular position and the final angular position and the initial angular position that the object during its rotation has traversed during a time interval delta t. So delta theta is equal to theta 2 minus theta 1, where theta 2 is the angular position at time t2, and theta 1 is the angular position at time t1, t2 minus t1 being delta t, the time of the motion. The angular velocity is now defined in terms of the angular displacement, as we did for the case of the one-dimensional translational motion. The average angular velocity is, we call omega. Omega average, omega bar, is defined as the change in the angular position divided by the time of interval during which the motion or this displacement has occurred. This is the average angular position, and as usual, the instantaneous angular velocity, or simply the angular velocity, dropping the word instantaneous, can be determined from the definition of the average angular velocity by taking the limit as delta t, the time interval for the motion, as it goes to 0. The limit as delta t goes to 0 is simply of delta theta over delta t is simply d theta over dt, and thus the instantaneous angular velocity, or similarly the angular velocity of the rotating object, is defined as omega is equal to d theta by dt. The angular velocity is determined in terms of units of angular of radians per second, because the angular displacement has units of radians, which is not really a physical unit, but a quantity of measuring the angle, and thus the velocity, since it's delta theta by delta t, then it has units of radians per second or revolutions per second, depending on how we measure the angular displacement, in terms of revolutions or in terms of radians. Or if we measure the angular displacement in terms of degrees, then the velocity, the angular velocity, will be measured in terms of degrees per second. The angular velocity is defined to be positive if the body is rotating counterclockwise, and is negative if the body is rotating clockwise. And this is because of the following. If we define the x-axis as being the axis relative to which we measure the angle, then going counterclockwise, the angle is increasing. As we go counterclockwise, the angle is increasing. Thus, delta theta is positive as we go counterclockwise. And since the velocity, the angular velocity, is simply delta theta over delta t, or d theta by dt, that means if we go counterclockwise, the angular velocity is positive. And similarly, if we go clockwise, if the body is rotating clockwise, then the angular position and the angular position is decreasing, and the angular displacement is negative, in which case the velocity is negative. The magnitude of the angular velocity, which is the angular speed, is also called omega. So omega would be either the angular velocity or the angular speed, the magnitude. The angular acceleration is also defined as usual if we have a rotating object if the object changes its angular velocity from one time to another, then we say that this object is experiencing an angular acceleration as it rotates. Angular acceleration means it is changing angular velocity. And the angular acceleration is defined as we did in the case of the translational motion in one dimension. First of all, we define the average angular acceleration, and we call it alpha. The angular acceleration is called alpha. Thus, we have alpha average, alpha bar on top of it, is equal to the change in the angular velocity divided by the time of the motion during which that change took place. So this is the definition of the angular acceleration. The instantaneous angular acceleration, or simply by dropping the word instantaneous, simply the angular acceleration alpha, is also determined as usual by taking the limit of delta omega by delta t as delta t goes to 0, in which case this quantity delta omega over delta t is transformed into the derivative of omega with respect to t, which is d omega by dt. Thus, alpha, the angular acceleration of the system at a particular time, is simply determined by taking the derivative of the angular velocity with respect to time. It's the rate of change of the angular velocity with respect to time. So knowing omega as a function of time, this allows us to calculate the angular acceleration. Or vice versa, if we know alpha as a function of time, then doing the inverse of this process, which is converting the differentiation into an integration, would allow us to obtain omega from alpha. So these are two correlated quantities in the motion, in the rotational motion of a rigid body. As usual, the units of the angular acceleration are determined from its definition, and it is simply radian per second square, because it is it's the second derivative of the angular position with respect to time. It's the first derivative of the angular velocity or the second derivative of the angular position, since the angular velocity is simply the first derivative of the angular position. So since that's the case, then the units of the angular acceleration is simply radians or revolutions per second square, depending on how we measure the displacement, the angular displacement. Rotation, thus, about a fixed axis resembles the one-dimensional translational motion of a particle. It is a very similar motion, but in the case of translational motion, we have the particle going along the x-axis, while in rotation about a fixed axis, we have only the angle theta is changing. In the rotation, the angle theta is changing, the angular position. In the case of translation, the variable x is changing, the position x is changing. So in each case, we have one component of the position is changing. In this case, theta, and in this case, we have x. So these two motions resemble each other, and they are very similar. The sign of the different quantities in the translational motion are defined in terms of how the motion takes place. For example, the particle is translating, is moving along the positive x direction or negative. So that's in the case of translation. What about in the case of rotation? In the case of rotation, we determine the sign of the direction of the angular quantities, or the sign, because we are dealing like with one dimensional rotation. Rotation about a fixed axis is like one-dimensional rotation around this axis. We define the direction in terms of plus or minus sign, just in the case of translation. And how do we define it? We use the right-hand rule, where we curve our hands, our fingers in the direction of the rotation of the object, and this would be the direction of that quantity. So if we have a delta theta, an angular displacement from this position to that position, for example, from an initial position to a final position, then we put our fingers along the initial position, and then we curve it towards the second position, and we find by this way that the upward is the direction of this delta theta, which is the positive direction. And this is consistent with our previous discussion that we are going counterclockwise. We are going counterclockwise, that means the sign is positive. That way we define the directions of the different angular quantities, whether it is the angular displacement or the angular velocity. Similarly, the angular velocity is determined in a similar way, because the angular velocity's direction is the same as the direction of the change in the angular position. It's the same as the angular displacement. So determining the direction of the angular displacement leads to the definition of the sign or direction of the angular velocity. And in a similar fashion, we define also the direction of the angular acceleration. If the velocity is changing in a positive way, that means if delta omega is positive, that means if from time t1 to time t2 omega increases, that means the acceleration is positive. And vice versa, if it decreases, the acceleration is negative. Now we arrive at the point where we can apply these definitions to the case of motion or rotational motion with a constant angular acceleration. As we have done, we follow exactly the same steps that we have followed in the case of deriving the equations of motion for a particle translating along the x-axis. Taking into consideration that this is like a one-dimensional motion, we follow exactly the same steps, and we would find the equations of motion for the angular rotation in exactly the same way, and the equations would look exactly similar to those for the one-dimensional translational motion. For example, let's look at this table. This table shows that the first equation in the angular case is omega equals omega naught plus alpha t. This equation is derived from the definition of the average angular acceleration. Since we have the case of a constant acceleration, angular acceleration, then we have the average acceleration is equal to the instantaneous acceleration. So alpha is equal to alpha average, and alpha average is simply delta w over delta t. So defining t1, the initial time, defining it to be 0, this will lead to omega, which is the final velocity, angular velocity of rotation, minus omega naught, which is the initial angular velocity of rotation, divided by delta t, which is simply t. that is the average acceleration is equal to the instantaneous acceleration. This is the case when we have a constant acceleration. The average is equal to the instantaneous value. So this will give us the first equation. Omega equals omega naught plus alpha t, and this is equivalent. This looks exactly the same way as v equals v naught plus at, with only replacing the linear velocity by the angular velocity and the linear acceleration by the angular acceleration, and we arrive at the same equation. The second equation, as we did in the case of the translational motion, is this one number 4 in the table, which is simply delta theta minus theta naught is equal to 1/2 omega naught plus omega into t. This equation, as we mentioned before, is simply the definition of the average velocity. The average velocity is defined in two ways. On the one hand, it's defined as delta theta over delta t, which gives theta minus theta naught over t. That's on the one hand. On the other hand, since the acceleration is constant, the angular acceleration is constant, that means the particle is rotating, is changing its angular velocity as it rotates in a uniform fashion. It changes it with an equal amount per unit time, which means that the average velocity during the time of motion can be taken as simply half the initial velocity plus the final velocity. That's like the average velocity. So in this case, we have the average velocity is defined in two ways. One of them is delta theta over delta t is equal to 1/2 omega naught plus omega, and from this we obtain this equation, which is theta minus theta naught is equal to 1/2 omega naught plus omega times t. And this is an equation that relates the angular displacement with the initial velocity, angular velocity, and final angular velocity and time. As usual, each one of these equations contain 4 different variables. If one of these 4 variables is unknown and the rest are known, then we can solve that particular equation and find that unknown directly. Now, those, however, are 2 equations that give us the facility to solve for one of the unknowns at a time, but the motion involves, as we said in the translational case, it involves 5 different variables, which are omega, omega naught, alpha, t, and delta theta, which is the displacement. So those 5 variables, to solve for each one of these 5 variables, we have to obtain 5 different equations, each one of them containing one of these variables as an unknown. So far we have 2 equations, and the remaining 3 equations can be obtained as we did in the case of the linear motion in one dimension by coupling these 2 equations, the one that we obtained from the definition of the acceleration and the one that we obtained from the definition of the average velocity, noting that they have 3 common quantities between the 2, which are omega, omega naught, and t. Those are 3 common quantities between the 2 equations. If we eliminate any one of these 3 common quantities between the 2 equations, we get a new equation. So eliminating omega in the beginning, we we obtain the second equation, which is delta theta equals omega naught t plus 1/2 alpha t square. Eliminating omega naught, we will obtain the last equation, which is delta theta equals omega t minus 1/2 alpha t square. And finally, eliminating t, we will obtain the third equation, which does not contain t, which is omega square is equal to omega naught square plus 2 alpha times delta theta. That way, we can get the 5 equations of motion that we can use to solve any problem that we have, and these are similar, very similar to the case of the one-dimensional translational motion. At this point, we have developed the methods by which we can calculate the different quantities relevant to the rotational motion of an object about a fixed axis, and by which we can fully describe the rotational motion of that body around a fixed axis. And at this point, I am finishing this lecture, and I thank you for your attention.